All right, so what we're going to do basically for each thing here, we're going to talk about the procedure, the name of the procedure. These are the ones, this first column, this is what you would write to identify the procedure that you're using in the inference stuff, okay? And then, so we're going to talk about that, and then we'll talk about the statistic and parameter, and I'm going to emphasize the conditions for each one, followed by where do you pick that out in the calculator, okay? So the very first thing we learned about was the one sample z interval for a proportion. In other words, I have a p hat to estimate p. Okay, and the conditions for that were random, normal, and independent. And the biggest piece here is that to check that normal condition, you are going to do np hat, and 1 minus p hat is greater than or equal to 10. Do we remember how to check the random and independent conditions? Just a quick reminder, if we have random sampling, we're going to have n is less than 10% of our population. If we have random assignment, then you're going to say individual responses are independent. Now, if it's a one sample, we use p hat to estimate p. If it is two sample, we use the difference between our two p hats to estimate the difference between our two population p's. And if that's the case, you got to check both samples. So anytime it's a two sample procedure, you're checking that normal condition for both samples. And you're making sure you're communicating that. In the calculator, you're going to choose the one prop z int or the two prop z int. Are we good so far? So, worth noting, anything that is a proportion is a z procedure. When it's means, we will do a t procedure. You guys, if I'm doing a one sample t interval, what is the statistic I would use? X bar, the mean of our sample. What would it be trying to estimate? Mu. Now, if what we have is something that came from paired data, like before and after, or a twin study, or somebody receiving both treatments, right? And what we do is we find the differences. We would still run we call it a paired t interval, but it's done the same way. Okay? Yeah. Those are D's.
Oh, okay. Sorry.
Because you would do a paired interval for the mean difference.
Oh, thank
Okay, what are those conditions?
Random,
Random, normal,
normal, independent.
independent. And the random and independent conditions are checked identically throughout all of these. You either have random sampling and you use the 10% condition for the independence, or you have random assignment of treatments and individual responses to those treatments are independent. Okay? What's the normal condition for means?
The population is approximately.
The X bars will be normal if the population is, but we don't know the population. So we typically look at either you have a graph with no major skewness, and if a graph doesn't have any major skewness or outliers, it's reasonable to assume it came from a normal population. Okay? Or what if we don't have any graphs? Or my sample size is greater than or equal to 30. This is what we really hope for.
Isn't it without major skewness?
I said no major skewness, right?
Yeah, I heard it and then I looked at it and I was like, oh.
Sometimes my pen is stuck on what I'm saying instead of what I'm thinking. Okay, and to do this one in the calculator, you do a t interval. Okay, only difference is if I have two samples, it's going to be x bar 1 minus x bar 2 to estimate mu 1 minus mu 2. One of the things that showed up a lot when you guys took the test over this is you would do a two-sample t-test for mu. And when you're doing a two-sample, you're not testing for a singular value. You're testing for the difference between two population values. Okay? And then we would do a two-sample t-interval. And again, anything two-sample, you've got to check for both samples. One sample, you just check the conditions. Two sample, you check the conditions twice, once for each sample. Okay, the last confidence interval we have is we did a used B to estimate beta, the slope of the population line. And what was our type of test with that one? What would it be? It would be a t-test or t-interval. And can you guys remind me what the conditions for the linear stuff was?
It was liner was the
Of all of the conditions, this is the one I am concerned about the least.
Is there lower likelihood they'll ask us about it?
100% lower likelihood. In fact, I don't know that I've ever seen this in a free response question.
That's
But they would say which of the following conditions are not met in multiple choice. Yeah, so I think you need to be familiar with the conditions, but
You don't have to know how to write it all out.
it's incredibly unlikely that you will. Like, is it fair for them to ask it? Technically, yes. However, I wouldn't stress too much about it.
no problem?
Do you guys remember what each of these stands for?
No.
Okay. The L stands for linear. You would look at a scatter plot and make sure that it's actually a linear thing. Because like if you're trying to estimate the slope of curved data, then you've got your own problems, right? Because the slope changes in curved data depending on where you are on the graph. Cool? I is the same and it has always been. Independent. Can I do this? I kind of got it to fit there. Kind of. Okay, what does the end? Normal. For the normal condition, we want the residuals to be approximately normal. E?
Equal variance.
Equal variance. That's the one where we look for no fanning on the residual plot. R is random. I don't know why I all of a sudden wrote the R horizontal.
Because it's random.
Oh.
Like,
Does anybody else feel the need to get some chocolate? Because that felt a little bit too lame.
is it chocolate?
I want chocolate now. Because your joke was so lame, I want
That
chocolate.
was good.
Thank you.
I would not have thought of that. Thank you.
I don't
But it's not random, it's horizontal. Random would look like this.
Okay.
But it's random.
It's random that
other
you
ones.
did that.
Yeah.
Not maybe like statistically random. Okay. That kind of makes sense.
That's just two diagonals.
Yeah,
So very
it
random.
can't be random because we can't.
Random.
We
It
can't
looks like a
randomly
sine and
brain.
cosine graph.
Randomly brain.
Yeah.
Yeah. Good thing you have chocolate. Yeah.
Hmm?
Good thing you have chocolate.
That is always. Even when the jar back there is empty, I got chocolate hidden away in lots of places in this room. It's really, for, you guys, I don't do it for me. I eat that chocolate for you. Because it's like, why do I drink coffee in the morning? It's not for me. I'd much rather not need it and sleep in, right? But since I'm here every morning, I would like to be kind. And coffee usually, helps. Hey, there is a ln reg t interval in the calculator. We never used it, nor do I think you guys need to use it. But it's there. You have to have the raw data in order to run it. The formula, otherwise, is you would take the sample slope plus or minus t star times the standard error of the slope, which you got from the regression table. And t star came from inverse t. A reminder, your degrees of freedom is n minus 2 in this case.
Is you said star and I kept writing star everywhere. And then I was like, why am I writing stars? The standard error, the
Mhm.
standard error.
Of the slope.
Oh, okay. So it's assumption.
Okay. Next we had tests. So these are all the confidence intervals. Now we're going to do all the tests. All right. If I am doing a one sample z-test for a proportion, my null hypothesis is going to be p is equal to some number, which I'm just going to leave as an x for now. But it'll be p equals something. Or you know what? I'll just do an example of p equals 0.2. That might be your null hypothesis. It might be p equals 0.5. It might be p equals 0.77. Everybody good? Mm-hmm. Okay. Your conditions are, in fact, random, normal, and anyone want to guess the last one? Independent. Great. Now, you guys, for this one, your normal condition, you use n, p from the null hypothesis, and 1 minus p from the null hypothesis. Both of those values have to be greater than or equal to 10. Random and independent, always the same. So what's super annoying is the normal condition for anything having to do with P really depends on what you're doing with P, okay? Calculator or function, you would choose the one props z-test. Now, something that happens every time, so I'm going to point it out real quick, okay? The name that you're going to write down on your paper or on your exam is the one sample z-test for P, okay? But when you open up that test menu in your calculator, there is a one sample z-test and then there's a one prop z-test. That is because even though we don't really cover it in this course, there is a one sample z-test for P if you know this population standard deviation. Okay? So, if you go to and choose one sample z-test, it asks you for a sample mean. It asks you for a sample size, right? But it asks you for stuff you do not have. That doesn't mean you should try to figure out what those numbers are. That means you pick the wrong thing and go back and pick the one prop z-test. Do you guys see what I'm saying there? Okay. My null hypothesis for a two sample z-test would be P1 minus P2 equals 0. Another way we might write that is P1 equals P2. Both of them mean the same thing. Does anybody want to guess what these conditions are? Random, normal, and independent. This should feel pretty annoying by this point, right? We'll get over those really quick. Okay, you guys, the normal condition, you do that NP and N1 minus P for both samples. So this becomes N1, N1. Then you do N2. Is everybody with me? And all four of these things have to be greater than or equal to 10. However, you guys, here I use the P for my null hypothesis. Do I know the value for each of these P's in the null hypothesis? No. So what we use is that combined P hat. Do you guys remember how to find P hat combined? It is on your formula sheet. It's the number of successes in the first sample plus the number of successes in the second sample. The size of the first sample plus the size of the second sample. In other words, it is as if you took your two samples and created one giant group from them. Okay? And the test we would pick in the calculator for this one is 2 prop z test. Okay. My null hypothesis for a t-test for a mean or a paired t-test would be either mu equals some number, or if it's paired, you would say mu d equals 0. Likewise, my null hypothesis will be mu1 minus mu2 equals 0, or you could write that as mu1 equals mu2. Both of those are fine. Conditions. Random, normal, independent. And the normal condition, you need n1 greater than or equal to 30 or no major skewness. If you have two samples, you have to do it for both samples. In the calculator, you choose t-test or two-sample t-test. T-test for slope, your null hypothesis is beta equals 0. Your conditions are the exact same. It's up. I'm sorry?
I said, should we write it before and then I saw it.
I mean, if you guys want to write it all out again, sure. I'll even give you the time and pull down the page so you can look and see what you had written above, so you're not flipping back and forth. I'm just not doing it. I don't know why I deleted this line. I've tried to undelete it, and it was becoming not a time-friendly thing for me to. Kind of, but to be honest, what I thought were that I was branching these ones, not.
Oh, wait, I didn't even realize that. Yeah. I thought those were the two.
Almost done, guys. Okay. I know I'm using a goodness of fit test when I have P1, P2, P3, up towards however many I have, okay? So it could be you have 4 categories, so then you would have a P1 for the first category, P2 for the second category, etc. Right? If you have 5 categories, P1, P2, P3, yeah, it's not the same. Yeah.
So I'm not taking the same test?
Yeah.
The test is not
Yeah. All right, your conditions, random. Large sample size, and how do I check that one?
10%.
The independent I'll check 10%. The large sample size,
Isn't all counts are greater than 5?
it's not all counts. It's the expected counts have to be greater than or equal to 5. Independent is checked probably 10% in this particular test. Because you wouldn't have like results from an experiment. So, chi-squared of homogeneity is separate populations or separate treatment groups. Most likely, the way you guys will see it is treatment groups, okay? So you're going to say the proportion of, so let's say what I have is, let's say what I have is an experiment where some group is taking a placebo and some group is taking a new drug for something. For cataracts or something. I feel like I always pick the same things, you know? Okay, then the proportion of cataracts is the same for both the placebo group and the treatment group. Then your alternative would be it is not the same. Do you guys see what I'm saying? Okay. All right. Your null hypothesis for a chi-square test of independence will be your first variable is independent from your second. Your alternative would be that it is dependent. Other ways we said that, you could also call this a chi-square test for association. Independent is equivalent to no association. So be your chi-square test could be there is no association. That could look like there is no association between blank and blank. Okay. Conditions for that. Both of these are run the same way, same conditions. Would be random, large sample size, and independent. And in the calculator, you choose the chi-squared test. It's a good bet that if you get a two-way table, you're going to be expected to use these ones. I misspell independent every time because I'm thinking faster than what I'm writing.